So again, as I mentioned earlier, in theory, this should all be reviewed, but let's brush off the cobwebs. A force is a push or a pull. That's a bad definition of a force. Really, a force is an interaction between two objects. Well, this is a good enough definition for physics 11, physics 12. If you push on something, if you pull on something, you're exerting a force. It is a vector, and that's going to become way more important this year. And it has a magnitude measured in newtons. Although, since F equals what? Since it's MA, a newton is really a kilogram meter per second squared, but we decided to name that a newton. Forces are based on interactions between two objects. You have to have two objects for a force to occur. In other words, if you're a spaceship out in the middle of the universe, away from anything, and you don't have any engines, there's nothing that you can apply a force onto. There'll be no force on you. Some important forces that we're going to study in this course include the following. These should be familiar to you. What was the name that we gave to the force that was the Earth pulling on all objects downwards towards the planet's center? We called that gravity. And the symbol that I used for that was a capital F and then a lowercase g subscript for F, gravity. What was the force that could best be described as microscopic hills and valleys between an object and a surface that interlock and prevent or impede sliding? That's a long definition for friction. My abbrev for friction was kind of weird because most textbooks just do FF. For some reason, I put the R there. It's about the only time in my life that I've developed the habit of writing an extra unnecessary letter, Zach. I don't know why I do it, but I do. Because you've had me enough to know I tend to abbrev pretty efficiently. Then we had this new one, this new concept or idea that we learned last year. What was the name of the force that was the surface pushing up on objects? We also called it the apparent weight, not the true weight. This was a normal force. Some textbooks, Danica, don't write this down, will use that for normal force, but that's also newtons and north. I'm looking at Page when I said, I don't know why. Page, I don't use that, but you might see that. I'm going to use that. F with a subscripted M. Maybe I told you this story last year. There used to be a provincial exam for Physics 12. And so kids would write the exam in June, and then the first week of July, a bunch of us teachers would get together at SFU and mark the exams, and I was on the exam marking committee for a couple of years. And so there was one question that said, find the normal force. And I was marking a paper and the kid wrote, which was funny, but they got a 0. So, I mean, at least they knew the abbrev, I guess. It was a start. What was the force from a stretched string or rope that was constant throughout the entire string or rope? What was the force that we called from a rope? Tension. Some of you are feeling it right now. Every time I cough. My little COVID cough is still sticking around. I really should use this, but I'm going to use this, and unfortunately, that's going to come back to bite us this year. This is where I'm a bad teacher, because I used a capital T for tension last year. Capital T this year means something in circular motion. It's the period. It's how long it takes something to go around once. And we will run into a situation where we have T tension and T period in the same equation, because Dweck is an idiot. Sorry. What was the contact force from an external agent, usually a person, or I often said invisible leprechauns? It was coming from off the page. the mystery force that was coming from off the page. What did we call that one? That was F applied. And I abbreviated that as F. What was the force of resistance from the air that was always acting in the opposite direction of motion? Air resistance, fancy word actually for you. And by the way, air resists. Can't even spell resistance, Mr. Duke. Air resistance is fine. Fancy word, by the way, drag. D-R-A-G. And then I often wrote F air, but air resistance is a complicated enough force. It really is. We tended to treat it kind of like friction, and we ignored it much of the time. I may have told you there's a standard physics joke. What's the most terrifying phrase to any physicist? Include air resistance. Really? Okay. Ooh, last one. It was not a force that showed up on your free body diagram. It was the vector sum or the resultant of all of the forces acting on the object. F something. And it's actually what I put on your formula sheet, because it's not F equals MA, it's something else equals MA. It's the net force, the combination of all of the force. And this year, because we're doing vectors, Braden, it'll be the vector sum of all of the forces. That's the net force, F net. That one never showed up on our free body diagram. When I did my winner minus losers equals shtick, the F net was the equals shtick, which never showed up in my free body diagram. It showed up in my calculations. Lies, 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 lies. Most of these are lies. In fact, there's only 4 fundamental forces in the universe, and most of these are combinations of these 4. So I have to put on my nerd cap, Mason, and say, look, what I've just told you is garbage. Although we're not going to dive down to these 4 fundamental forces all the time, I have to at least be honest. What are the 4 fundamental forces? Well, gravity is. So Fg is legit. Although Einstein made an argument that gravity is not actually a force, but a curvature of space-time. So if you're a general relativist, you might argue, yeah, there's only 3 fundamental forces. The 4th one is a curvature of space-time. And why would you call a curvature a force? Point taken. There's something called the strong nuclear force, sometimes just called the strong force. This is what holds the nucleus of an atom together. You learn maybe in Science 9 that like charges repel. Protons are like charges, and they are repelling each other. What prevents the nucleus from flying apart? The strong nuclear force. You know what? Not only is there a strong nuclear force, but there is a weak nuclear force. The weak nuclear force helps explain things like radioactive decay. Both nuclear forces, strong and weak, they act only over very, 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 very short distances, about the diameter of an atomic nucleus. In one way, none of you have ever felt the strong force or the weak force, except since you're all made of atoms. Of course you have, because if the strong force and weak force weren't there, nuclei couldn't stay together, atoms would not be atoms. The 4th one is electromagnetism. This is the force that basically explains pretty much everything else. Normal force, tension, they're actually electromagnetism. So, for example, let's look at what we call the normal force. It's actually electromagnetism. I might have told you this last year, but it bears repeating. If you take your non-writing hand, push down on your lab table right now. as hard as you can. Are you touching your table? No, none of you ever have touched anything. Now, we would say that the table was exerting a normal force against your hand, preventing your hand from sinking, and you can think of it that way. But really what's happening, Owen, is the electrons on the outer atoms of your hand are repelling the electrons in the outer atoms of the table, and as you get closer and closer and closer, like charges repel, and we'll actually look at the electrostatic force and how to calculate it, and you'll realize, oh, there's an R squared on the bottom. Those are there in calculus. As that R gets smaller and smaller, the force gets bigger and bigger until eventually it gets so big that I can't go any further. My nerves treat that as, oh, you're touching. I'm not. If I had an electron microscope, you would still see a gap. Last year we learned about Newton's laws. I went on my Sir Isaac Newton rant. What was Newton's first law? Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied. Basically it says this: the only way that you can accelerate an object or change its velocity is to apply an unbalanced outside force. If an object is accelerating, Zach, there has to be an unbalanced force. If an object is not accelerating, the forces must be, and looking for a word that starts with the letter B, balanced. That's Newton's first. This is often called the law of inertia. Pause the video for a second. Newton's second law is the equation. F equals what? Yeah. Force equals mass times acceleration. By the way, Newton never wrote it this way. He was much more interested in something called impulse. So he wrote it like this: F equals mass, change in velocity over change in time. And this concept here, mass times change in velocity, is called impulse. And the symbol for impulse is change in momentum. Last year, I never got to momentum. This first semester I did, and so some of that might vaguely look familiar, but that's F equals ma in disguise. Newton's third law is often called the law of action-reaction. It's usually stated something like, for every action there is an equal and opposite reaction, which I never understood. What's Mr. Duix? Forces come in. Forces come in. I guess technically I should say opposite pairs. As an equation, the force of object A on object B is going to be negative or opposite the force of object B on object A. You can't push without getting pushed, is another way I've heard it phrased. So I think I have... So, based on this then, why would an athlete want low mass shoes? So especially, why would a sprinter want low mass shoes? What would your lighter make any difference? Why? I've just said low mass, so I agree low mass shoes would have less mass. Thank you, Captain Obvious. Also, circles are round. Okay. Can we... Yeah. F equals what? Get the A by itself. What does A equal then? Good. So let's suppose, Braden, you're a sprinter and you've done a workout, you've lifted weights. You can't increase your force anymore, but you still want a better acceleration off the start. What else can you change in this equation? In fact, the smaller the mass, the bigger the acceleration, right? Ooh, another thought puzzle. Let's suppose that Kai and Aiden are astronauts on the International Space Station. We can dream. And they're inside the space station, so they're not wearing their spacesuits, but they're doing some repacking in the cargo hold. And Kai decides to send a heavy 25 kilogram object floating across the cargo hold. And Aiden, rather than catching it, he decides to stop it with his face. In 0G, will that hurt? Or will it just bounce off and no harm, no foul? Kai is nodding. Convince me, astronaut Kai.
You still have a force on you, which is gravity.
You do? Which is what?
Gravity.
Let's pretend you're in outer space, no gravity. Way outer space. Braden. F equals what? Everybody, F equals what? Let's get that. Well, even if we're in 0G, does this object still have mass? Yes. When it hits Aiden's face, will its velocity change? I'm going to ask the same question. I want the same answer. I'm just going to phrase it differently. When it hits Aiden's face, will there be an acceleration? Well, if we got a mass and we got an acceleration, what else do we have? Darn right we got a force applied to Aiden's face. It'll hurt. We have ma, so there is force. That's actually really, really important because that also means you can use a hammer in 0G. Otherwise, the hammer would just bounce right off and do nothing. Right? Hammer still has mass, and when it hits the nail, it will accelerate. It'll apply force. A force with which you have had some experience is the force of gravity between you and the Earth. This force is also known as weight. Your mass is not the same as weight. I like the fact that somebody said, well, mass and weight are different. They are. Mass is measured in newtons or pounds in the old system. Oh, I said mass is measured in newtons. Weight is measured in newtons or pounds in the old system. So weight is a force, and in the old system, in the imperial system, pounds are a unit of force. What are the SI units for mass? What do we measure mass in? What are the old imperial units for mass? No, pounds is a force. Just said. By the way, which means when you stand on a scale, it's kind of weird. Kilograms is telling you your mass. Pounds is telling you the gravitational force, although a scale is doing none of those things. We'll talk about that in a second. The imperial unit for mass is slugs. If you'd read ahead, you would have noticed that, just saying. To relate mass to force, we need to know the number of newtons of force per kilogram of matter. This quantity is known as gravitational field strength. We called it something different in Physics 11. Near the Earth's gravity, the Earth has a gravitational field strength of 9.8 newtons per kilogram. What did we call that 9.8 in Physics 11? What was that 9.8? The acceleration due to gravity. Okay. Ready? Yes? Don't write this down. And when we were talking about gravity, yes? Get the A by itself. Get the G by itself. So, Danica, this must be equivalent to an acceleration because of F equals ma. But we're going to start to refer to this also as newtons per kilogram gravitational field strength. Can you see how I got the newtons per kilogram units for this? Newtons per kilogram and meters per second squared, mathematically they're identical, but Paige, what you're going to start to notice is when I talk about a gravitational field strength, I'll talk about it in terms of how many newtons it's pulling on every kilogram of mass, because that's a nice way to think about gravity. But it's also how fast you'll accelerate in a vacuum in that gravitational field strength, because F equals what? Ma. If you get the A by itself, you get F over M. So Earth has a gravity field of 9.8. Moon's is about 1.6. So we have the force of gravity is mg. It's a vector, but towards the center of the planet is usually the direction, so I'm not too fussy on your vector symbol. Example 2 says, all right, find the weight of a 10 kilogram object A on the Earth or B on the Moon. Well, weight is the same as mg. Weight is the same as mg, except I guess I'm going to use g on the Earth and g on the Moon. Zach, in this question in A, what's the mass? What's the gravitational field strength of the Earth? Which is what? Wow, this is maybe the first time ever. I don't know if you saw what I was doing. I was scanning the class for someone who was dumb enough to be doing this on their calculator, and I didn't see anybody. Looked like you all did that in your head. What about on the Moon? Okay, it's going to be 10, Zach, not times 9.8, but times what? The gravitational field strength of the Moon, which I think I gave you in the previous paragraph at the end there. The Moon's gravity is When the astronauts were on the Moon, did their mass change? What changed? How hard gravity was pulling on them, their weight. And that's why they were able to wear object spacesuits that weighed several hundred pounds on the Earth in relative comfort on the Moon. Oh, and we did land on the Moon, people. Alrighty. Example 3. We get to vote again. It says this. Select the best answer. If a force of gravity acts on an object, then the object A remains at rest. B moves at a constant speed. C accelerates in the direction of the force. Or D may remain at rest, move at a constant velocity, or accelerate. We're going to vote. How high you hold your hand up is how sure you are of the answer. So if gravity is acting on an object, who says? Do okay. Remains at rest. I don't know. So, if the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the gravitational force, or D, all of the above. Okay. Who says easy? A. It's got to be A. A. Who says B? Of course, it accelerates in the direction of the force. Who says all of the above? I saw one person kind of look around and then join the all of the above. So we'll see if that was a thinking vote or a peer pressure vote. George, convince me. Okay, convince me.
I feel like there's it's on the table.
Okay, so for A can be true, what? What am I? All caps. Object on desk. I agree. Can you give me a way that B can be true? You can be moving at a constant speed, but also be under the influence of gravity? Maybe. You need to elaborate. I will say this. I've experienced it, although most of you haven't. Have I mentioned something lately? Because I should have mentioned something lately. What about Scott? Okay, but I'm accelerating, or am I?
No, you're staying at a constant speed.
Well, initially I'm accelerating, but who remembers the term that we used to describe it when my air resistance was the same size as gravity? Okay, if you hit terminal velocity, you can be moving at a constant speed under the influence of gravity. What about accelerate in the direction of the force? Oh, well, how about free fall? Or free fall in general, as long as we have a fairly aerodynamic object and don't let it hit terminal velocity, which is what we pretended was happening most of the time last year. So, D. The two of you that voted for C, if I convinced you? Okay. Newton's first law says if we have balanced forces, objects at rest remain at rest, objects in motion remain in motion. If we have unbalanced forces, then there's an acceleration. If we have balanced forces, no acceleration. That means you're either going at a steady speed or you're at rest. If we have unbalanced forces, you must be accelerating. Oh, and spoiler alert, in the same direction as the unbalanced force. We write it like this. F net, or the sum of all the forces, equals the net force. And again, F net is not a force that's going to show up on my free body diagram. It's the vector sum of all the forces. So don't ever label F net on your free body diagram. Also, I think I mentioned this already. I did a little dance with you, Danica. Newtons per kilogram and meters per second squared must be the same thing because G equals F over M, which also is acceleration. Newtons per kilogram and meters per second squared gotta be the same thing. So another term for acceleration due to gravity that I'm going to use more and more this year is gravitational field strength measured in newtons per kilogram. Modern physics has a branch or a sub-branch called field theory, which is hugely important. More and more physics at the upper levels is being taught in terms of fields are causing everything. A gravitational field is what causes gravity. An electromagnetic field is what causes electromagnetism. An energy field explains how energy transfer occurs. The Higgs field explains why objects have mass. Example 4 says find the unbalanced or net force. In each case, include direction. Let's put a little compass rose right here. Oh, wrong button, Mr. Duke. And let's zoom in. What's the net force, magnitude, and direction on A? Well, I'll give you a hint. 2 newtons. Direction. Yep. At east. What's the net force, magnitude, and direction in B? Magnitude, please. How big? 3.7 newtons at direction south. Ooh. The first N is newtons. The N after the at symbol is north, and I may have mentioned that we're running out of letters in the English alphabet because we are. They reuse them. Okay. By the way, then, which way must C be accelerating? North. Which way must C be moving? I can't say. I need more information because it might have been going south really, really fast. Accelerating north means it's just slowing down. Or it might be moving north and speeding up. I don't know. I need more information. Acceleration doesn't tell me which way we're moving. It only tells me which way we're accelerating. Ooh. Darman, someone's just spoken already. 5? Let's see. 8 right, 3 left. Yeah. F net equals 5 newtons. Direction? East. E. First of all, what's the north-south force? And what does that mean? That means there's 2 possibilities. It's not moving north-south at all, or it's moving north-south at a constant speed. Just humming along. I don't know which. Okay, I just know it's not accelerating. Horizontally, what was it? 7 newtons at east. No, west. Mr. Duick, west. So this object is accelerating to the west. It might be moving north-south at a constant speed. I don't know. It may be moving east and slowing down. I don't know. How would you find this? Yeah. Y minus X newtons south. And this is last year, winner minus loser. I was really sneaking that in as vector mathematics. Hey, Mr. Duick, what if the forces are at angles to each other? Oh, did I say angles? Everybody? Components. We'll get there. So to solve force problems, what did we do last year? We used something called a free body diagram, or an FBD. We put one arrow for each of the forces, roughly to scale. What do I mean by roughly to scale? If I knew force A was bigger than force B, I would make sure it was obvious, longer arrow. If I knew 2 forces were identical, I would eyeball it, make them the same length. My friend who teaches at Kwantlen, which I borrowed these notes from him, he also has his students sometimes add velocities or accelerations as like squiggly lines or dotted lines. I'm kind of a purist. I leave my free body diagrams with forces only, usually. So we're going to use the free body diagram to write an algebraic net force equation, kind of like we did here. We're going to solve for any unknowns. Our net force equation will be derived by using a tug-of-war analogy. We're going to ask ourselves, which force is winning? And then we're going to use, remember this from last year or last semester? Winner minus loser equals, well, F net, but on your formula sheet, what's F net equal to? So instead of saying F net, we jump straight to MA. This allows us to avoid having to decide which way should be positive, which way is negative. We're going to let positive be whatever makes the math the nicest. Example 5. A 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. A says, Mason, what does A want me to do? Free body diagram. I'm going to do it, how about right here? Mason, what are the forces acting on this rock? Get the obvious one. Which way? And I know the force of gravity is calculated by mg. What else? Acceleration is not a force, so it's not going to go on my free body diagram. That's both a good guess and a bad guess. But let's talk about acceleration. Which way does this question tell me this rock is accelerating? Which way does there have to be a bigger unbalanced force pointing? Which way does this question tell me the rock is accelerating? Say it again. I want the same answer to the next question. Your line is up. Which way does that mean there's a bigger unbalanced force pointing? I know there has to be a force a bigger force up. Tension. The cable. So A says draw a free body diagram. B says compare the forces. I did both in one step. I compared them with my arrow lengths. Mason, who's winning? Who's the loser? Nick, you didn't see. I said, who's the loser? And he looked at you. You know what? Bonson Park. You can take him. 3 o'clock. Gravity, fine. What does winner minus loser always equal? Okay. What's D you want me to find? In this question, they gave me the acceleration and said find the tension. As far as I'm concerned, I could also give you the tension and say find the acceleration. I could give you the tension and the acceleration and say find the mass. There will be 2 M's. We'd have to figure out what to do with that, but we'll talk about that later on this unit. For now, they want me to find T. How would I get the T by itself, Mason? Which one of those is correct? Plus the mg over. MA plus mg or mg plus MA. Doesn't matter because we're adding. All right. Ooh. What's M? Is it 2,000? How do I know that 2,000 is not a mass? What is that 2,000 then? This is mg. So, okay, not 2,000 times 9.8, just 2,000 plus. And Mason, what's the acceleration? How can I find the mass? And I'm so lazy, I'm just going to go 2,000 divided by 9.8 in the actual equation, and I'll do it once on my calculator and walk away. What do you get? I'll go to 3 sig figs, 2610 newtons, because it's a force. Ooh, we get to vote again in example 6. So example 6 says this: is it correct to say that if the rock in example 5 is moving upwards, string tension, 2,610, must always be bigger than the weight of the rock? We're going to vote. How high you hold your hand up is how sure you are of the answer. So, true or false? Is it correct to say that as long as the rock is moving upwards, tension's going to be bigger than the weight? Oh. Who says, yeah, true, Mr. Dewitt, true. 1, 2. Who says, no, false? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Who didn't vote? You voted? What did you vote? You did? I missed you then. What did you vote? I know. What are you voting? What are you voting? Got pick. Thank you. Get my dart back. Did you vote? What are you voting? So we've got, okay. It's a little better. And I missed one more that didn't vote, but I'll find you next time. Convince me. Yeah. The rock could be moving upwards, but it could be accelerating downwards. How the heck can that be? Hey, you know what? Let's go for an even simpler case. What if If A equals 0, then we're moving up at a steady speed. Now, if A equals 0, that means the forces must be, I'm looking for a word that starts with letter B. If we're moving up at a constant velocity, then gravity equals tension. And this question said, does tension always have to be bigger than the weight of the rock? Nope, not if it's moving at a constant velocity. They're equal, which is not bigger. But now Kai has opened up a little bit of a can of worms. So example 7, is it ever possible for the core tension to be less than the weight of the rock? Well, I guess if we were accelerating down, because then gravity would be the winner. How the heck can we be accelerating down? We're moving up, but slowing down. Okay? So the answer here is, yeah, you actually predicted where I was going. And how? Moving up, but slowing down. And you can put in brackets, accelerating downwards. So that means mg is winning, tension is losing, tension is less than mg. Okay. Little technical comment. So if the mass in example 5 is accelerating down, we have two choices. We could let down be negative the whole time. Nah, we're going to let positive be whatever makes the math nicer. Okay? And now we come to a thought puzzle, my tricycle demonstration. Pause the video. So for those of you following at home, the homework I assigned, every question, but you can skip number 6, number 8, and number 10. Skip number 6, number 8, and number 10. Sorry I was talking so long.